So our next example is where Chapter 5 gets a little bit tricky. But like I said before, the torsional members are just like the axial members. And so an indeterminate torsional problem might seem complicated on the surface, but fundamentally you use the same exact process that you would for an indeterminate axial member that we went over in Chapter 4. So we have two different ways that we can solve indeterminate problems from Chapter 4. One is the force or flexibility method, where we remove a redundant support, and the other is the stiffness or displacement method. For this example, we're going to go over the force flexibility method, but you could solve this problem either way. And so to introduce the problem, here we have a circular shaft. It's supported between two fixed supports at points A and B, and then at intermediate points C and D, we have a torsional moment applied at each. We have a 500 Newton meter external torque applied at C, and in the same direction we have a 200 Newton meter torque applied at point D. The dimensions are given. We're also told something about the material. We're told it is A36 steel, so we can look up the modulus of rigidity for that from the back of Hibbler. And we're also given the constant cross-sectional diameter across the entire length of the shaft is given as 60 millimeters. So we're going to use that to calculate the polar moment of inertia of the cross-section. So again, we know that this is indeterminate because we have two supports, one at either end. We know that combined these support reactions at point A and point B have to add up to completely withstand the moment at C and D, but we just don't know how much is going to go to support A and how much of this applied torque is going to be resisted by point B. So again, statics gets us part of the way. It tells us that combined support A and B will resist this entire 700 Newton meter moment. But again, strength of materials is what's going to tell us exactly how much goes to A and exactly how much goes to B. And that's going to allow us to solve for the required portion of this problem, which is trying to get the maximum shear stress at any location across this shaft. We need to figure out what the maximum torque is. And we can't figure that out until we've solved and reduced the indeterminacy of this down to a point where we can calculate the torque in every single section. So just like with the other torque problems, I find that the isometric 3D view can be a little bit confusing. And so first we're going to reduce this down to a two-dimensional view. We'll use the right-hand rule to turn these three-dimensional moments into two-dimensional vectors to make the statics a little bit easier. So our first step is simply to draw this as a two-dimensional free body diagram. And so we're going to take this isometric view, we're going to draw the horizontal shaft. We have points A, and again the labeling of the points is a little bit odd here. It goes A, C, D, and B, which is fine, we can deal with that. So here we have the geometry. I should write down the dimensions to each of these different points, and that's given as 1 meter, 1.5 meters, and 1 meter from D to B. We have the points labeled. We know that the shaft is fixed at A. It is also fixed at B, so I'll show the supports right there. And then at points C and D, we have to show our applied moments. And again, this is where we're going to use the right-hand rule. So we take our right hand, we rotate our fingers in the direction of the rotation that's shown, and then whichever direction our thumb is pointed by tracing that moment is the direction of the two-dimensional vector that represents that moment. So here, this would not be the correct direction. This is going the opposite direction of the rotation. I have to turn my hand upside down for my fingers to curl in the direction of the shown rotation or the shown torque. And so here, both of these have a vector with the sense to the right. So my two-dimensional moment vector is going to be pointed to the right. So at each of these points of torque application, I'm going to have a double-headed vector pointing to the right, and we get 500 Newton meters at point C, and we have 200 Newton meters applied at point D. Okay, so that's essentially just redrawing this given diagram right here, and we're going to use this to reference back to the given information throughout the problem. Okay, so at this point we really need to figure out which method we're going to go with to solve for the indeterminate problem. Like I said, you have two different options, just like with axial members. We could either use the force flexibility method, which is where we remove one of these supports as redundant, and then we try to figure out, well, if the support wasn't there, how much would this shaft rotate at that point? And once we have a number for that in radians, then we calculate, well, how much torque would be, how much of a support torque would be required here to counteract that rotation completely. The other option is to do the stiffness displacement method. And with that methodology, we would look at equilibrium first. We would figure out the relationship between all of the internal torques and the applied torques. We'd find that we don't have enough equations to solve for all the unknowns. We'd only have one equation. We'd have two unknowns in this situation. And so after the equilibrium step, then we need to figure out the compatibility step. We'd draw another diagram and we'd say, we know that the overall rotation of this shaft between points A with respect to point B, we can't have any overall rotation of those 2 points relative to each other because they're both fixed. From that compatibility equation, we can then relate it back to torques using TL over JG, and then we'd be able to solve the two equations simultaneously to solve for the two unknowns, which would essentially be the torque in member AC, the torque in member DB. For this tutorial, we're going to use the force or flexibility method. If I have time, I'll also work through this problem doing the stiffness displacement method as well too, but either would work just fine. And again, the steps that you take are pretty much identical to the axial members in chapter 4. So if we're doing the force and flexibility method, then step number 1 is going to be compatibility. And again, we're doing the force flexibility method. Okay, so our first step is to select one of these supports as redundant, and then we'll remove it to create what we call a primary system. We'll investigate two different loadings on that primary system. The first, we'll keep the externally applied loads. We'll see how much rotation would occur where we remove that support. And the second loading, we would put a torque, a support torque at the free end where we remove the actual support and figure out what magnitude would be required to completely counteract the rotation that we calculate for the first type of loading. So here we have a choice to make. We can either remove the support at A, we could remove the support at B. Either way would be fine. The only criteria is that whatever support you remove, it has to remain a stable system. Here that wouldn't be a problem with either support. I'm just going to decide to remove the support at A. It's somewhat of an arbitrary decision. I don't think it would make the math any easier either way. So if I remove the support at A, I'm going to draw my new primary system with two different loadings on it. So we will have the shaft with a free end at A. The support at B will remain. And I'm going to draw that system twice. Because again, what we're saying based off the principle of superposition is that this system here with a support at A is equivalent to this system with the applied loads plus this system with a support torque at A. When they are combined together equals 0 rotation or 0 angle of twist at the free end A. So again, we're going to have two different loadings and we're just going to add the effects together based off of superposition. So here's my primary system with no support at A. And again, the first investigation will have the applied loads, the applied torques in this case. And the second investigation of this primary system is going to have the support reaction, the support torque at A. So here's point A. We have C, D, and B. A, C, D, and B. And with the first application, we're going to apply these external torques, 500 Newton meters, 200 Newton meters. I'm going to show the torques in red. And so we have 500 Newton meters. We have 200 Newton meters. Okay. And with green, I'm going to show the rotations that we're trying to keep track of. Again, it's a little tough because my rotations and my moments are both going to be represented by double-headed vector arrows. So I'm going to try to keep it clear with the color, but also put a little dash at the end of the rotation to make it clear that we're talking about a rotation and not a moment itself. Okay, so I want to keep track of the rotation at point A because we know in reality when we add these two systems together, that rotation at A has to equal 0 if it's going to truly be the same as this system, the true system over here. So I'm going to keep track of the angle of twist at point A due to the externally applied torques. And I'll put a little dash at the end of this. Hopefully that'll make it clear that we're talking about a rotation here with this green vector, whereas these red vectors we're talking about an actual torque being applied. Okay, so that's system number 1. We'll come back to that and we'll do the calculations for that in just a second. I will put the dimensions on here because that will end up being important. It's 1 meter, 1.5 meters for the middle segment, and 1 meter for the end segment. Okay, so now we need to look at the loading with this, the second type of loading on the same primary system. So we're no longer applying these externally applied torques. What we're doing is we're adding a support torque at point A that's going to mimic what the actual support at A does. So even though this is free to rotate, any torques that are applied here are causing a displacement. It's just that in the fixed system, that rotation, that displacement, is completely counteracting what the system wants to do if the support wasn't there. So here we're going to actually apply a torque on this second system at A to mimic the actual support itself. And so I'm going to say here that this is my torque at A. And we're also going to keep track of the rotation at A due to this support reaction. And so we're also going to keep track of the angle of twist here due to the reaction at A. So this is the angle of twist at A due to the support reaction. All right. And we have the dimensions shown up here. I'll show them down here. It's kind of redundant, but that's fine. 1 meter, 1.5 meters, and 1 meter. And again, notice on this secondary loading, we only have this kind of placeholder support reaction. We don't have any of the externally applied torques at all, just this one to mimic the support. So before we start calculating any torques with this system, we need to figure out the relationship between both of these so that they superimpose, so they add up to have 0 displacement here at A, 0 angle of twist here at A. And so the way that we do that, we know that if I were to add up both of these torques here, add up both these angles of twist here, I know they would have to add up to 0 because that's the known condition of the angle of twist here at A relative to B. And so basically what we know, the compatibility condition itself, we know is the angle of twist at A. Implicitly, this is angle of twist of A relative to the support due to the externally applied torque plus the angle of twist at point A due to the support reaction R. Those have to sum up to 0. And so now all that we have to do is we have to figure out, well, how do I relate the angle of twist at A due to each of these loads? How do I go about calculating those? That's where we use mechanics and materials. And then once we have that, one of these is going to be a discrete value, say for example 0.01 radians or something like that. That's going to be this one because we know what the torques are, we know what the material properties are, we know what the length is, we know what the section properties are, we're going to get an actual amount of rotation out of this first system. Again, like I said, it might be maybe 1/100th of a radian. Then this second term, the angle of twist due to this support torque, that's going to have an unknown, which is actually just the support torque itself. So we know the length, we know the sectional properties, we know the material properties. So everything will be known in this term except for that support torque T sub A. And so we'll be able to solve for that because it's one equation and we end up with just one unknown. And so the way that we go about that is our general equation for the angle of twist for either of these is going to be the sum of TL over JG. Here this will be for the external torques. Here we'll have the summation of TL over JG for the system that's only subject to this reaction, the torque reaction. And so all that I need to do for each of these systems is figure out what's the internal torque in section AC, CD, and DB. And then I know the lengths, I know the section properties, or I can calculate it very easily. We know what the modulus of rigidity is because it's A36 steel. We'll look that up in the back of the book. And then we can solve for this, and same thing over here with the second term. And so we're just going to split up each of these calculations, and we're going to look at up here at the top for the first system, we're going to sum TL over JG for this system that's subject to the external torques. Okay, so to figure out the internal torques, it's just like any other problem of this nature. We're going to make section cuts through each of these segments so that we can figure out what the constant torque is between A and C, between C and D, and between D and B. Okay, so I guess we can go through each of those kind of step by step. I'll draw the diagram, and then we'll keep track of the values up here because in terms of space, I'll run out of room. So I'll do the diagrams here. We'll keep track of each of the torques. Actually, we could probably make a table as well, too. That would probably help things out. Actually, we don't need to do that. It's not that complex of a problem. So we need to figure out what the torque is between AC, what the torque is between C and D, and the torque between D and B. And so all that we have to do for each of those is just make a free body diagram and then run the equation of equilibrium. So between A and C, I make a section cut there, and our free body diagram between A and C is really straightforward. We have some portion of the shaft. We have a section cut right here. I'm going to draw my internal torque pointed away from the section cut. That's torque AC. And we'll have one coordinate system that applies to all of these free body diagrams. But as you can see, the only moment that we have on this diagram is just the internal moment. And so if I were to sum the moments about the x equal to 0, the only term that I'm going to get is just the torque between AC. That has to be equal to 0. So that's really easy. The torque between A and C is equal to 0 because there's nothing else in the free body diagram. Okay, now let's do section CD. We'll get a little bit more out of that. So if we have section CD that we're looking at, I'm going to make a section cut between C and D, and then we'll draw our free body diagram, which has a little bit more. We have our section cut here between C and D. We're going to have our internal torque, which we always draw away from the section cut, and that's going to be the torque between C and D. And now we actually have an externally applied torque here, which is 500 Newton meters. That is pointed to the right. Okay, so we have the torque, we have the 500 Newton meters of torque externally applied. And now all that we need to do is we have our coordinate system, and we're going to run our equilibrium equation to solve for the internal torque T sub D. So if I sum that, I'm going to get positive 500 Newton meters. That's only because this is pointed to the right. Torque CD is also pointed to the right, so that's going to be positive as well. That's all going to be equal to 0. I just get the torque CD on one side by itself. And I get that the torque between C and D is equal to negative 500 Newton meters, just based off the Freebody diagram and equilibrium. So we can put that up here, negative 500 Newton meters. All right, that does it for section CD. So I'm going to erase that, then we're going to go to section DB and calculate the last internal torque. Okay. So here, section cut between D and B. I can choose to keep the portion of the shaft to the left of the section cut if I want, or I could take the section to the right. I'm just going to be consistent and keep on taking the portion to the left. So my free body diagram now, it's a little bit longer because we're cutting it further down the shaft. I have my section cut right here. I always draw my internal torque away from the section cut, and this is the torque between points D and B. And I want to draw my external torques on here now too. So I have 500 Newton meters to the right, just like I did before. I have 200 Newton meters to the right, which is a new torque that I haven't seen on my free body diagrams yet so far. And that's it. I just have to run the equations of equilibrium on this. I'm going to sum the moments about the x-axis equal to 0. And I get positive 500 Newton meters plus 200 Newton meters plus torque dB equals 0. And we find that I get, well, I'll run through the equation just for fun. It's positive 500 Newton meters plus 200 Newton meters plus torque dB equals 0. So I get that the torque between D and B is equal to negative 700 Newton meters. Okay, so I can put that up on my table now. I get negative 700 Newton meters. And I have everything, well, just about everything to solve my summation of TL over JG for this first loading condition. So I'm going to erase this free body diagram here. We have a couple minor calculations to do before we can run that equation. So we have all of the T's, all the torques. I would look in the back of my book to find what the shear modulus is. And I believe in this case our shear modulus is 75 gigapascals for A36 steel. So that's 75 times 10 to the 9th pascals. So we have G, that's taken care of. All of the lengths are provided for the problem. So length AC is 1 meter, length CD is 1.5 meters, and length DB is 1 meter. So all the lengths we have as well too. So we just have one minor calculation to do for the polar moment of inertia. Here it's relatively straightforward because this shaft is prismatic. It's the same diameter of the circular cross section the entire length. We're told that the diameter is 60 millimeters. So our calculation for J for a solid cross section, that's a circle, is pi over 2 times the radius to the 4th. So here we have pi over 2 times 0.03, which is half the diameter is the radius, to the 4th. And we get that J is equal to 1.27 times 10 to the negative 6th meters to the 4th. Okay. All right, so that's going to set up the rest of our calculation a little bit later on. I'm actually going to do both of these calculations at the same time. So we have all of this ready for us to go, and we'll combine these both in one long calculation in just a second. All right, but that's all of our placeholders that we need right now. Okay, one thing that I would mention is that because the torque in member AC is 0, we're only going to have 2 terms out of this summation because the torque in the very first term for member AC is just going to be 0. So we'll get 2 terms out of this. Makes it a little bit easier. Okay. And actually, I can start writing some of that down here. Like I say, because, again, we've been calculating this term right here. It's a summation of TL over JG. But because the first term is going to be 0, this will end up being TL over JG for member CD plus TL over JG for member DB. And those are for the externally applied torques. So we just get 2 terms out of that. And we know it's going to be added to the angle of twist due to just this support torque that we're applying in the second scenario to point A. Okay, so this one's a little bit more straightforward. Again, our formula is a summation of TL over JG for our angle of twist. But in this case, we don't really need to do a summation at all. The easiest way to figure that out is to first look at what our internal torque is going to be. So if I were to make a section cut between A and C, or between C and D, or between D and B, I'll get the same exact value for the internal torque. There's no intermediate torques here, so it's going to be a constant torque the entire distance. So let's just say anywhere on the member, just between points A and B, my free body diagram is going to be really straightforward. All that I have is my externally applied torque at A, at point A. I have my section cut, and I have my internal torque. And assuming we're using the same coordinate system as before, again, it won't make a difference for our final answer, but just in terms of summing this up, if I were to sum the moments about the x equal to 0, all the vectors pointed to the right will be addition, all the vectors pointed to the left will be subtraction. I get negative T sub A plus the internal torque capital T is equal to 0, or in other words, the internal torque is simply equal to that support reaction torque at A. All right, so no big surprise there. It's relatively straightforward. Again, it's still important to remember that we care about the internal torque. Often the internal torque is going to be equal to the single applied external torque, but it's not always going to be the case. For example, if we were to have drawn this torque at A pointed to the right, this would have been the internal torque is equal to minus the torque at A. And so it's important to get this step where you relate the internal torque to the external torque, even though it seems kind of nominal. So we have a constant torque the entire distance, and we've just calculated that it's going to be unknown at this point, but we just have 1. And so for the entire length, we don't really need to do a summation anymore, because it's a constant J the entire length, and it's a constant G the entire length as well too. And so it's really just one term in this case, and so it's going to be, when we talk about the length, it's just the length AB, and so we'll have the external torque at A, that's equal to our internal torque, times the length AB, that's the entire length of this column, all the segments together, divided by JG. And again, JG will be constant for all of these terms right here. This will all be equal to 0. And so now all that I need to do is just plug in our values, for example, for length AB, for J, and for G. Those will end up factoring out if we really wanted to. We could multiply both sides by J and G if we wanted to. Just cancel those out completely because it's a common denominator for all of these terms, which makes life a little bit easier. And so I don't have room below this, but I'm going to free up a little bit of room up above it to finish this calculation and put in our values. Okay, it will be helpful to have J later on, but it turns out that G doesn't really make any difference. What we have here, the torque times the length of member CD. So the torque in member CD was negative 500 Newton meters. The length of segment CD is 1.5 meters. Okay, then we add this term. The torque in member DB is negative 700 Newton meters. The length of segment DB, we just look to our given information, is simply 1 meter. Plus the torque at A, which is our unknown, times the length of the entire length of our shaft AB is 1, 2.5, 3.5 meters. That's all equal to 0. So all that I have now is one unknown. I just get that on one side by itself, and we find that the torque at A is equal to 414.3 Newton meters. Okay, so that says that in our original system, out of these 700 Newton meters of moment that get externally applied, over half of those go to A. I guess, just doing a reasonableness check, does that make sense? These moments are equally spaced from the supports. It's 1 meter from the support for each of them. So I would think that if both of these moments were the same, say both these moments were 350, I would assume because the geometry is spaced out evenly, and because the material is the same, I would expect if these were both 350 Newton meters, that half would go here and half would go here. But because the moments themselves are offset or off balanced, I have more moment over here close to A than I do have close to B. So it makes sense that more than half would go to A. So again, reasonableness, that makes sense. Okay, so we have our torque at A figured out. So now step number 2, I'm going to erase a little bit. I'm going to erase a lot, I guess. And I'll summarize what we did for step 1, and then we'll look at step 2, which is somewhat nominal when we're talking about the force flexibility method. Almost all of our work for the force flexibility method comes in step 1. And then step 2, oh, I shouldn't have erased J. And step number 2 is a little bit more nominal, but it's important in this situation. So step number 1, our big conclusion was that the support torque at A is equal to 414.3 Newton meters. That was our conclusion over here, right? Step number 2 is equilibrium. So we know that the torque at A, and I can draw that on here now. We now know that the torque at A is equal to 414.3 Newton meters. So at that point, we've essentially made this a determinate shaft. We've figured out one of the unknowns, so now if we were to run an equilibrium equation, we'd have one equation and only one unknown left over, which is that torque at B. So that's all that I'm going to do here to determine the torque over here at B. All that I'm going to do is run equilibrium, kind of what we call global equilibrium, on this entire free body diagram. So all that I need to do at that point is I'm going to draw a free body diagram. I'm going to show the externally applied torques, 500 Newton meter, 200 Newton meter. I have my support reaction. I guess green's okay. I have my support torque here of 414.3 Newton meters. And all that we're trying to figure out is the support reaction here. I can draw this away. And this would be the torque at B. If I have a coordinate system, that'll allow me to sum up these moments about x equal to 0. And so what I end up with would be negative 414.3 Newton meters, because that's pointed to the left, plus 500 Newton meters pointed to the right, plus 200 Newton meters pointed to the right, plus the torque at B all equal to 0. And what we end up getting is that the torque at B is equal to negative 285.7 Newton meters. That just means that the sense of this vector is actually in the other direction, which is fine. Okay, and once I have all of that, I've solved for the entire length of the beam. I don't have any unknown reactions at this point, so I could draw a torque diagram if I wanted to. I can make a section cut through each of these locations, and I could solve for what the internal torque is at each point. I'm not going to go over that. We've done a couple of videos. We walked through that process. It's relatively straightforward. But what I am going to do is I'm just going to use the graphical method, kind of the shortcut method, to draw my internal torque diagram for this system with the known reactions. So again, we know this is equal to negative 285. Actually, I will switch this around just for purposes of our graphical method here. We know it's going in the opposite direction because I had a negative value. So torque AB is equal to positive 285.7 Newton meters if I draw it in the opposite direction. And again, to avoid the confusion, I'm just going to erase this right here. So if we have this as our loading diagram for the shaft, and I want to plot out my internal torque across the length, we're going to use that shortcut that I was talking about. And you'll see this shortcut or something similar for chapter 4 when we're talking about normal force members. You're going to see this similar method in chapter 6 and 7 when we're talking about beams as well too. And so we have our points A, C, D, and B. And the methodology for that is pretty straightforward. We just simply, any vectors pointed to the left, that's going to be a jump up in the torque. So from here, it's going to jump up 414.3. So this is positive 414.3. Right here, I have a vector pointed to the right, 500 Newton meters is going to drop down 500. So 414.3 minus 500 is going to give us negative 85.7 Newton meters. Again, this is torque in Newton meter. At this point right here, we go down another 200. And then we'll go back up 285.7. So this value has to be negative 285.7. Okay, so this is all my internal torques across the length of the shaft. And so now all that I have to do to calculate the maximum magnitude of shear stress is, we'll call it step number 3, to get tau max, that's equal to TC divided by J. And we're just going to pull the largest magnitude value of the internal torque. In this case, that's 414.3 Newton meters. So I'll put in 414.3 Newton meters times C, the radius. We're given a diameter of 60 millimeters, so I just divide that by 2. I get 0.03 meters for the radius. And then J, we had calculated it up here before. That was equal to 1.27 times 10 to the negative 6th meters to the 4th. That's going to be our denominator. 1.27 times 10 to the negative 6th meters to the 4th. And I get a value of 9.79 megapascals as the largest magnitude of shear stress in the shaft.